Let's talk about the substitution rule. So in first semester calculus, we will learn about two integration techniques. Two integration techniques. Okay. The first one is what I call change the way it looks. And usually in this class we're using algebra to do that. In second semester calculus, we're going to use trig identities to do that as well. And the second method is the substitution rule. And that's really what I want to talk about with you all today. Okay. Now, when we have this integral sign of f of x dx, but you don't have any limits of integration over here, this is the antiderivative of the function f of x. So we also use that very same notation to describe something we call an indefinite integral. So these two things are exactly the same. The antiderivative is exactly the same as the indefinite integral. Okay. When we do integration by substitution, this helps us find the antiderivative when the integrand is the result of a chain rule derivative. So the integrand is just this inside function over here. So that's just, the integrand is really just this f of x. Okay. So this method is called substitution because we replace part of the integrand with u and part of the integral with du. So what we're really doing is we are changing the variable. Now, using substitution is really one of the classic math tricks that we have. So let me tell you about the substitution rule with indefinite integrals first. So let's say you have some function u equal to the g of x, where the derivative g prime of x is continuous over an interval, and let f of x also be continuous over the corresponding range of g. So this whole discussion is because we're working with a composition of functions, okay? And let f of x be an antiderivative of lowercase f of x. Then we will have the following. So when I go to write my integral, it's going to look like this. It's f of g of x times g prime of x dx. So my original problem has this really kind of complicated looking structure like this. And if you look at this inside part, this integrand looks like a chain rule type situation. Okay. Then what we're going to do is we're going to change the variable. We're going to integrate f of u du. And the substitution that we're going to make is we're going to have u is going to equal to the g of x. Okay. Then watch what's going to happen. I can differentiate both sides of this substitution with respect to x. So I can have du dx is equal to g prime of x. And then when I treat this du dx as a quotient of two differentials, I can really multiply both sides by dx. And I'm going to get du is equal to g prime of x dx like that. So now I hope you can see that the g of x right here has been replaced with the u, and that comes directly from my substitution. And the g prime of x dx part, that g prime of x dx gets replaced by du, like so. Then what I'm going to do next is I find the antiderivative. And we had already just said that the antiderivative of lowercase f is going to be capital F of u. And we always have a family of functions resulting, so this will be plus c. All right. And then finally, we would substitute our u back, so we'd have f is equal to g of x plus c. So the great thing about the substitution rule is we can always check our answer. If you took the derivative of this left-hand side over here, you should get exactly the integrand of our original question. So let's take a look at example 1, and this would be a great example for using the substitution rule. So when I look at this example 1 over here, I see I have x squared minus 5 cubed and then multiplied by 2x on the outside. Now your first instinct might be to multiply all of this stuff out, but we're going to use substitution instead. And what I'm going to do is I'm going to replace this somewhat complicated expression inside the cubing function. I'm going to call this part here u. And the great thing is I see the derivative of this sitting off to the side right here. So that's a clue that I'm going to be making the substitution. So let's try this. What we're going to do is we're going to let u be equal to the x squared minus 5. Okay. Then when I take the derivative of both sides, I get du dx is equal to 2x. And that means if I solve for du, I get du is equal to 2x dx. And I hope you all can see that that's exactly this part on the right side of my integral right here. So now I'm going to make my substitution, and I'm going to get the integral of u cubed du. Now this will be easy enough for me to integrate. That's just going to be u to the 4th over 4 plus c. But I don't want to leave my answer like this because my original question was in terms of x. So I really want to change all my u's back to x. So then I'm going to get quantity x squared minus 5 raised to the 4th power over 4 plus c. So let me highlight that because that's going to be our final answer. But we can always check our answer by taking the derivative. So let's check. So I'm going to differentiate 1/4 x squared minus 5 to the 4th power plus c. And I'm going to need the chain rule for that. So when I bring the 4 down, that's going to cancel with the 1/4 in front. So I'm going to have x squared minus 5 to the 3rd power. But according to the chain rule, I need to multiply by the derivative of the inside, and the derivative of the inside is going to be times 2x. And a quick look shows us that this derivative is exactly the same as the integrand. So we know that differentiation and integration are inverse processes. So if I find the antiderivative and then I take the derivative, I should get the original thing on the inside back. All righty, everyone. We're going to do a lot of examples in class together. Take care.